All right, great to have all of you here this morning. So without further ado, let's begin. For gravitational part 3, right, we are already talking about gravitational potential energy and the concept of potential. So let's start off with a recap. Hang on. Yep. So let's recall back what does conservation of energy, right, tell us about how the total energy of a system may vary. Okay. So you see, you think about total energy of a system, right, as money in your pocket. Okay. You may have two pockets, which is a left pocket and a right pocket. Okay. So one of it is KE, one of it is PE. So if nobody take money from you, or you didn't earn a living by doing some work for other people, then right, the total amount of money in your pocket will be constant. Okay, so total energy, right, of the system is a constant value until, right, there is a exchange in work. Okay, for example, you do work for other people, right, people give you money, so your left and right pocket, right, will have total increase. But it doesn't tell you about which pocket increase by how much, or is it both pocket will increase. Doesn't tell you anything about that, but you know total will increase. Okay, vice versa, right? If you pay money for someone to do work for you, maybe you'll say, okay, can you help me move these things, okay, downstairs? I give you $5 for that. You see, I'm paying money to get work done for me. Then, right, the amount of money I have will decrease. If you understood this, right, you're in good state, because this is the underlying foundation, right, for understanding a lot of things in physics. Yeah. So the net work, right, done by an external force is equals to the change in total energy. So this network could be a positive quantity. That means, right, you do work for other people pay you to do work. Okay, so your wealth will increase. Yeah. But it could be negative also. On the whole, right, some people pay you to do work, but you spend more. You pay other people to do work even more. Or let's say when you go out for a dinner, you pay for $20 dinner. You're actually paying the restaurants, right, and the chef and whoever, right, to do $20 worth of work for you. Yeah. So that is the idea. So and you must break it down further, right? This work can translate into total energy change, and that breaks down to two accounts on left pocket and right pocket. So sometimes, right, while your total money, right, your total wealth may decrease, but it could well turn out, right, that one of your pocket actually have more money. Okay, it's actually the other pocket, right, that sacrifice more. So overall, you are poorer, but one pocket has more money. It means that the other pocket lost even more. Yeah. Also, right, if we kept one of the pocket, right, zip up, okay, so we don't allow that pocket to change, so that change in one pocket, right, will be zero. Then it means, right, that all the input and output, right, will come directly from the pocket that is unzipped. Okay, yeah, we're pretending that the pocket have the zip, or like my the berms that I'm wearing now got this zip, okay, for the pocket. Okay, so with that, right, let's look at some cartoon. Okay, let's look at some cartoon. This is the creepiest cartoon in human history. It's called Teletubby, and I have no idea why this was made to be a show for kids. Okay, the last lesson, right, we have learned that near Earth's surface, gravitational field lines, right, looks like this. Just a recap. You see, the equal spacing tell you that the field strength is equal, which is true. Okay, whether you're at home now or I'm here where I am, we experience the same G 9.81. And also, right, the lines are parallel, means that the direction is all the same, or it's all pointing down, whether is it at your location or at my location, or up on a building, or up on a building, right, still close to a surface enough. Next, right, let's consider this Teletubby 2 kg. What's the force, right, experienced due to gravity? 20 Newton. Okay, so we have more Teletubbies here. They are all identical, so they have all the same weight. Now, right, if we were to draw these yellow lines, right, 1 meter apart from each other, right, we can actually assign, right, a potential energy value to each of them. And you are familiar with doing this already on your MGH. So, right, if we call the ground level 0, the first Teletubby will be 20, and so on and so forth. Or the fifth one will be 100. Yeah. This assignment of the values, right, first and foremost, is arbitrary. Okay. So anywhere, right, you can assign it to be 0. And you probably know this from last time. You could have assigned it this way. The top guy, right, you call it as 0, and the bottom guy, right, just 1 meter above the ground, call it as minus 80. This has no impact on how, right, you work out potential energy change. Because, right, if you take the red Teletubby, right, up to the highest level, you will have a change in potential energy of 80 or positive 80. Same as the case, right, previously, whereby you assign this value. Okay, you go from 20 to 100 is a plus 80. You go from a minus 80 to a 0 is also a plus 80. So you can see from this, right, the assignment of 0, right, is arbitrary. Yet, right, the selection of this 0 is not so trivial. Yeah, it makes good sense, right, that we actually assign a sensible 0. For your normal solving of the problem, right, it doesn't matter because, right, your equation is easy to work out, and normally, right, we don't talk about potential energy where it's 0. You always, right, in a problem solving, you are just choosing assign this place to be 0, but that is not the real value, or it's just a relative value to facilitate your calculation. So if you want to choose a point, right, that you designate as real 0, right, you have to be more careful in doing so, or have to bear more considerations. Okay, next, right, we also can know that each line means 20 joules. Okay, so therefore, right, we can start to say that these lines, right, represent these values of potential energy. Okay, for the Teletubby. It's not generic. Okay, it's just for the Teletubby. Yeah. Now, right, suppose I want to have, so we put the lines there, right, just for reference. So we know these are the potential energy levels of the Teletubby if it were to be on this list. Suppose, right, now we want to compare, sorry, if we want to now move Teletubbies along, right, okay, and let's say, right, I want to move the red one from position 1 to position 2. I therefore know, right, that in doing so, I will incur, right, a work done of 80. Okay, why is it 80? Because, right, to be able to just leave the Teletubby, right, my external force needs to be 20 Newton, just equals to the weight. Yeah, and you know, by the definition of work done, or force times displacement in direction of force, so the work done by this force will be 80. Just nice, right, that you see the change in potential energy, right, is also 80. Okay, does this surprise us? I hope not. Okay, because, right, we have just gone through the formulation of conservation of energy. The work done, right, the net work done is equals to change in total energy. But now, right, in this process, we actually don't want the Teletubby to speed up or slow down. We let it start from rest, let it end at rest. Or you can think about it as, right, let it start with a non-zero speed, it's already moving. You apply a force, it continue to move up without a change in speed because the net force is 0. There's no change in speed. So the Ke pocket is being zipped up. All the work that you do deposits into the potential energy pocket. Okay, so the change in potential energy is equals to the net external work. Similarly, right, for the other guy, the yellow one, you move from 1 to 2. This time now, right, you see that the displacement is downwards, but your external force is upwards. So what is the work done by this force? It will be minus 40. And what's the change in potential energy? Also minus 40. So you can see, right, that the net work done equals to change in potential energy. This formula, okay, is validated by these two guys. Yeah, but it's just an example. Yeah. Now, right, let's scale things up. We look at the scale, right, whereby things are, the gravitational field is varying. So we are no longer talking about a uniform field, but a non-uniform one, or when you're far away, far enough from Earth. So let's take position 1, right, as infinity here. Okay, this is the starting position. And position 2, right, at somewhere near Earth, okay, inside Earth's gravitational field. Going from position 1 to position 2, right, okay, this process, right, involve this Teletubby, right, experiencing greater and greater gravitational force. Thus, right, if you want to bring this in without it speeding up, okay, that means we have to zip up the Ke pocket. We need to apply an external force, right, that is equal to the weight at all time. Okay, does it make sense to you? Or if we want to bring this object, right, from infinity inwards, and we don't want it to speed up, then, right, the necessity is we provide an external force equal to the weight. Now, if we use the formulation from just now, the change in potential energy, right, equals to the net work done. Okay, net external work done. It doesn't matter whether I say the external or not. Okay, but yes. Then, right, we furthermore put infinity as 0. Okay, just like how we put the highest yellow line as 0 just now, we put infinity as 0. Then what does it mean? It means, right, that moving from infinity to any point, okay, the change in potential energy, right, will simply be the potential energy at that point minus infinity. So far, you get it? Oh, and you see that the Gpe at infinity is set to be 0. Then, right, the potential energy at that point is just the net work done. Yeah. At first, we say that it's a change in potential energy is net work done, but now because your start point, right, is 0, so the final minus 0 is just the final. Oh, so we are saying now that the final is equal to net work done. So you see, why do we get this thing? It's because, right, of our assignment. We assign 0 as the Gpe at infinity. Therefore, in Gpe at any point, right, will be equals to net work done in bringing the object from infinity to that point. Okay, and that is essentially, right, the definition of Gpe. Oh, you see, you've seen this before, right? And this always tested, yeah, because it's a important definition, and a lot of concepts, right, surrounding Gpe stems from this definition itself. Now, let's understand this a bit more. So this Gpe, right, I'm just repeating the formula here. See, is the net work done? Then now you have to investigate, right? What is the nature of this work? The nature of this work, right, is that it is brought about by the external force, which is pointing outwards, but the displacement is always pointing inwards. Okay, so that means, right, that the work done, right, is always negative. Okay, because Fg is always attractive. Am I right? Fg is always attractive. So your external force, right, has to be always opposite to Fg. Since, right, this process that we described is from infinity to somewhere near, so it's always an inwards process of the displacement is always inwards. Yet your force, right, to prevent it from speeding up, the external force is outwards. Therefore, the work done is a negative work. Okay. Now you relate it to the previous statement. We are saying that the Gpe at a point, okay, is equal to the work done by external force, bringing the mass from infinity to that point. Therefore, right, we are saying Gpe is negative. You understand so far? So this entire slide, right, contain all these points. Okay. First point is why the work done, right? The first point, right, is the orange box. Okay, which is right what we have done in the previous slide. Let me just go back just to recap. See, the previous slide we talked about this. So we're saying that net work done is equals to final GPE minus initial. That one is a general statement from WEP. And previous slide we also say that let's take infinity, right, as 0 GPE. Then, right, this slide we go on and say, right, since gravitational force is attractive, so what can we say about the external force? It must be opposite in direction to gravitational force. And the external force is also opposite to displacement. So this work is negative. Okay. This is a question that always come up, asking you explain why GPE is negative. Yeah. This whole past 5-10 minutes, right, is worthwhile recapping to yourself. You must do it for yourself, right, one time, without referring to anything. Run through the logic. If you find yourself don't know what's going on, refer back to this video for the explanation, then reason it out to yourself until you can reason out, okay, with no problem. Then you have mastered this portion. Once you master this portion, you'll feel very much at ease because, right, it now makes logical sense to you. Because, right, it is made up of many logical pieces, right, of the puzzle. And all these logical pieces, right, come together to finally, right, give you the conclusion of why is GPE negative by its formulation. Yeah, a lot of people struggle with this. They merely memorize. So if you don't want to memorize, right, you must seek to understand. Yep, let's talk about the design of the GPE a bit more. You can see, right, that if that is the case, then, right, ignore the formula first, but I'm just going to give you a formula. Later on, we can actually come about, right, showing why the formula is as such. That GPE, right, will be biggest at infinity. Okay, infinity is king. Everywhere else will be negative. This graph, right, only show you GPE due to Earth, assuming that Earth is the only thing that leads to some substantial gravitational pull. But in a real universe, right, there could be many planets nearby, many stars nearby. Doesn't matter. So as long as you are in the vicinity, your neighborhood got many planets, right, the GPE of a body, right, that is there will always be negative. As long as you experience gravitational field, your GPE will be negative. The only way, right, that you have 0 GPE, which is the biggest, by the way, is when you are not experiencing gravitational field. You are free. When you experience gravitational field one way or another, you are trapped. You are going to be put, okay, in one direction or another, in the direction of the gravitational field. So 0 is king in our system here. Okay, therefore, right, if you want to get to 0, you always need to increase your potential energy because you always start from negative. And that is also, right, coherent with our pre-gravitational understanding. Before you do this gravitational topic in JC, you already know, right, lifting something upwards away from center of Earth, okay, opposite to the direction of gravitational force. You know that by mgh, the higher it is, the more potential energy it has. It's the same, nothing different. In a normal sense, right, you're bringing something further from the center or from the source of the gravitation. Similarly, right, the more you bring something away from the source of the gravitation or towards infinity, i.e., the higher the GPE. Okay, now, right, let's derive this thing. This part is very mathematical. You don't actually need to do it, but I think you can appreciate it because you have all integrated 1 over r square, 1 over x square function before. Or when you integrate a 1 over x square, right, you get a minus 1 over x. Yeah. So let's see how this works. Let's look at the graph of the F external force. Okay, F external force, right, is equal in magnitude to the weight, and we draw the F external, right, in a positive direction. Let me also draw the weight to show you. The weights, right, will actually be a graph, right, that's in this zone. Okay, and why is it negative? Is because of the convention that you set. Because we are saying, right, going away from Earth, or the R means, right, in any given direction away from Earth is positive. You see, that's what this arrow is implying. Or whatever the direction the arrow points to means that this is the positive direction. Okay, thus, right, relative to this convention, F external is a positive force because it's like away, whereas Fg is negative. Oh, in some textbook, right, you will see Fg being drawn as negative. They will write Fg equals to minus Gmm over R squared. Sorry. Why so? It's because, right, is to represent Fg is attractive. Fg is attractive, right? It is always opposite in direction to the R. Yeah. Okay, back to our story here. So we know F external, right, is like that. And we take, right, infinity to be 0, okay? And hence, right, the potential energy at any point, right, is simply the work done and is area under the graph, okay? How do we find out what is the area under the graph? We integrate the force with respect to R. We start from the initial. You see, this is the initial. This is the final. Final is R, initial is infinity. So you integrate this 1 over R square function, you get a minus 1 over R. Yeah. Now, right, you substitute in the limits to this R here. But since it's a negative, right, you can think about it as flipping. So you are substituting, right, the infinity and R into the 1 over R. So you have infinity minus the 1 for R. This gives you, right, simply just this term. No, because the first term, right, disappears. It is 0. 1 over infinity is 0. Yeah, so there you have it. So this is how potential energy formula come from. Okay. Just a quick concept check to make sure that we understand what's going on thus far. Yeah, so how do we know what is the potential energy of this system? Which one is the lowest? We can just use this formula, okay, and see. In fact, right, the system B, right, has higher potential energy. You see, the uninitiated will say, oh, A has more energy. Not correct. Because it's a -2. -2 is smaller. On the graph, right, less negative means bigger. So system A, right, is lower in GPE. And you notice, right, this question didn't ask which object has a lower GPE. It asks, right, which system has a lower GPE. Why so? Because, right, GPE, right, always arises from a interaction. Oh, I can't write it with my mouse. Okay, GPE, right, is always from a pair. So two masses, right, attract each other, and when they are near each other, right, there is a particular GPE associated with this interaction. They attract each other, so got one GPE. Suppose, right, you have, we illustrate this point, right, using this example. Suppose you have 3 masses, and we have to find what's the GPE of this system, right? So we'll know, right, that there are 3 set of interaction altogether. So let's call this 1, 2, and 3. So 1 attracts 2, 2 attracts 1. So this 1 interaction. Okay. 1 attracts 3, 3 attracts 1. This is a second interaction. 2 attracts 3, 3 attracts 2. That's a third interaction. Therefore, right, there is one GPE associated with each interaction. Okay, not with two body, but with each interaction. Usually, right, when normally we do questions, right, we always think about the Earth and then an object, okay, and this object like move away, okay, to somewhere, right, and then we say the GPE of the object increases. Not quite true, okay. I mean, you say that in exam, we won't penalize you, but that's actually not correct. It's actually right, the GPE of the object Earth system, yeah. Which is why, right, you don't consider the work done by weight, because weight is not an external force. Weight is an internal force, and your system is always object and Earth, or moon and Earth, or moon and object, Earth and object. Yeah, it's always come in a pair. So it's only a third party pull it, right? Then it's considered an external force. Yeah. So let me erase this. How do I erase this thing? Never mind. Oh, can erase all ink. Done. So another way of thinking about this problem, right, is to ask, since right GPE is the work done in bringing blah 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 from infinity to 1 point, or that's for a particular mass, right, or just for one interaction. So we have multiple one. So let's just expand this formulation and this thinking, right, into the work done, right, in bringing the masses from infinity to this setup. So they are coming from different points in infinity. I mean, infinity is so big, right? So they are just coming from different points and meet in this setup. Yeah. So while they are at infinity, right, they don't feel each other. So you assemble these three masses, right, from that particular start state whereby they are far away from each other. So first, right, start with bringing one guy in. Okay. So when you bring the first guy in, right, so yeah, I'm here. So what? Nothing happened. Oh, because right, there's no gravity with anything else. Nobody near it. So right, is there any work to be done? Don't have. Yeah. Now right, first guy is in place. We bring in a second guy. Okay, from another corner of infinity, you bring it in. So now is there any work? Yes. Okay, and that work right is equals to the potential energy of 1, 2. Okay, and why do we say that it's the work? Because right, we want this particle 2 right to come in without speeding up. So there is a external force, right, opposite to its weight, to the gravitational pull, right, or that's holding it back, prevent it from speeding up. So now it's in place. Then you want to bring a third guy in. This is where it gets complicated. Now you have two guys, right, exerting gravitational pull on the third guy. So how do you know what is the work done? Because right, see, when there are two masses, right, there are like two forces tugging it. Oh, so it's not easy, right, to figure out what's the external force really. But never mind, because right, you can still think of that work done, right, as being done separately by one force and by the other force. Okay, the effect is the same. Therefore, right, you can just plus the two terms together. Okay, and you note that the on the outside, right, am I missing something here? Gravitation potential. Hey, where's my negative sign? Unfortunately, right, this whole thing is a bit problematic. But I'll add it in. So I should have a minus sign here, and minus sign here. So finally, when I add it up, it'll be like this. Okay, so that is the GP of this system. It cannot be positive because right, they are under the influence of each other's gravity. As we said, when there is a presence of gravity, the GP of a system will always be non-zero. It will be always negative. Sorry, yeah, cannot be 0, 1, or cannot be positive because 0 means right, no gravity felt. Okay. Let me pause for a while. Any questions thus far before we go too far? No? Actually, I pause for me to drink water. So if you have no question, we'll move on. Okay, let's try this example, quick one. So how can we get the formula, right, that we are very familiar, which is mgh, from the current new formula that we learned, which is minus gmm over r, okay? And it starts from, right, considering where the object is. So, right, we start off at a point near Earth's surface, okay, which is like this point here. Then, right, we are moving it by a short distance h. How short is this h? Few hundred meters, few kilometers, also okay. By and large, right, that is the acceptable range for h, maximum limit. Yeah, but in our normal problem, right, it's always a few meter or tens of meter, so it's no problem in this context. So let's consider, right, using the formula and find out what's the change in potential energy as we leave it up. So we just use final minus initial, because that's what the meaning of change is. So we substitute in the final, okay, final, right, you will have the r plus h as the denominator, initial is just r. You manipulate the terms around, look at this. So now, right, you take out all the common term, which is the gm, okay, you put it on the outside. Yeah, are we missing something here? Yeah, we are missing something here. Where's my small m? Ew, got another mistake. I'm so sorry. Yeah, so here you should expect another small m. Okay, yep, but otherwise it's okay. And hence, right, from here, you note that let's say we want to combine the two fractions together. So to combine, right, you have to multiply the denominator of the other fraction. Yeah. So this is what we get as a result. So now we combine. On top, right, you will have r cancel out with the r. At the bottom, right, you will have r multiplied by a r plus h. R plus h, right, is almost equals to just equals to r. Because, right, relative to Earth radius, this h is very small. It could be 1 km. Oh, but look, Earth's radius is 6,400 km. So it doesn't matter, right? It's 6,401 or 6,400. They are about the same. Therefore, right, you can rewrite the bottom as a r square. Okay. Now let's group, right, the terms, right, together. So you have, right, gm over r square grouped together. This gives you g, which is the field strength near Earth's surface. M, you take it out, H, you put it at the back, and there you have it, mgh. Okay, so no conflict. These two things, right, are both correct. Okay, but, right, the mgh is an approximation, is not the real thing. It's an approximation you use for calculating changes. You can't use it to calculate absolute value, but you can use it to calculate changes. And we are always happy with changes because, right, that's what we are concerned with when we are doing a process, right? We are interested in final minus initial. We are not so interested in what's the absolute value. Yeah. So this formula mgh works well enough. A next example is escape speed. Okay. How do we go about thinking about escape speed, right? Is this whenever, right, you're on Earth and you think of life here, right, getting boring, you want to escape, right? What can you do? You can jump, right? Or you can make a jump. Except that your jump, right, can only elevate you by a few meters, a few meters, a fraction of a meter, okay? Or we can't get too far. So let's say, right, you take some supplement, okay, you manage to jump higher, but that's still not good enough, okay. You want to escape, right, means you want to jump to infinity. That's how high you want to go to. So that's the question, what is the speed that you need, right? so that you can jump to infinity. Okay. Another way of thinking about it as let's say you have a wall. Okay, high jump the bar. So you want to jump over it. Okay. Now, right, and you want to just spend the minimum amount of energy to cross this. So the way that you do it, right, will be to work out what is the GPE you need, right, to get to the top. Yeah. And you don't want to waste energy. So you will want to just have enough KE at the beginning to reach the top. You don't want to cross it and still going up. That means, right, you have made too energetic an attempt. Yeah. But now, right, this wall that we are talking about is like so high. Okay. So high that is like infinity high. So you're trying to jump over it. But guess what? As you reach this top of the wall, right, which is infinity, you have managed to successfully escape. Okay. Thus, right, we want to ask, what is the minimum energy, right, needed to escape? We do that, right, by considering the initial energy first. Initial energy, right, the KE that you need to jump with will be just half mv squared. The V is unknown. We want to find out what is the value. Your GP is just the formula minus GMM over R. Where will you land at? You'll land at infinity. Your KE there, right, will be just nice 0, because you see that's the situation that we're talking about, right? You want to make just enough a jump, right, that managed to cross the top of the imaginary bar, but this bar happens to be at infinity. Yeah, so you don't want to reach that bar, right, with excess KE, because you'll be wasting energy. We are talking about what's the minimum you need to do. So when you reach there, right, you just nice KE 0. Also, right, by the formula, GP is also 0 at the top. So total energy is 0. So for infinity, right, you can actually know something about your total energy, which is this value. Suppose, right, in the whole process, you didn't lose any energy, there was no work done, yeah, then, right, your initial total energy will be equals to the final total energy, will be equals to 0, yeah. And now, right, we are curious to solve for the initial speed. So you equate initial 1 to 0, you'll get something like this, and you solve for V. So the first version, right, straightforward. That's what you get from solving, simplifying this equation. The next version, right, that you get on is by shuffling the terms around. We have a GM over R. What if, right, I want to have a GM over R squared, okay, instead? Then it means, right, I need to times R outside, okay? And why is GM over R squared special? Because, right, this gives us G. And this is good, okay, because we know this is 9.81. It's a well-known value. Or if you're talking about from surface of Earth, right, this is a well-known value. So see, this formula, right, become even simpler to interpret compared to let's say this one. Actually, both are straightforward. Both are straightforward. It's not too difficult. Okay. So that gives us, right, the formulation of escape speed. Next one, next example, right, is yet a very common thing that you see all the time, which is talking about energy of satellite. This draws upon our knowledge, right, in the gravitational 1 and 2, okay, about circular motion due to gravity. So circular motion due to gravity, right, centripetal force is provided by the gravitational force. This one always need to write. So this is the equation that you can form. It's a F equals to ma. Then you simplify this, or you make mv squared the subject. Why do we want to make mv squared the subject? Because, right, we want to obtain ke. Ke is half mv squared. So once you get to this step, then you times a half. That gives you, right, the formula for ke. And let me stress, right, this one is only for satellite. Okay. or anything that's orbiting Earth. You cannot use this for anything else, okay? Because, right, see, how do we get this? We get this, right, from this premise, or from this equation. So it arises because of a circular motion. So you cannot use it out of context. And we see, right, Gm over R is Gmm over R is familiar. It's just Gpe. So this Ke is also equals to minus half times of Gpe. So that's how we get it. Now, right, you want to find out what's the total energy. You can do it already because it's equals to Gpe plus Ke. And well, voila, you have it. Okay, it's also equals to it's also can be expressed in terms of Gpe. Is half Gpe. So together you sketch them, they'll appear like this. Ke and total energy are identical, mirror image of each other. Gp is like double. So you draw the value, right? The Y value at every point also greater than the Y value at for total energy. Yeah. Things to note here. Here, right, are all finite value. Because, right, you're talking about a finite non-zero R, which is R at the surface. That's the smallest radius a satellite can go, just above the surface of Earth. Therefore, right, the value is a finite value. It's not asymptote. Now, right, let's make things a bit more interesting. So far, we are talking about gravitational potential energy, right? Being work done on a real mass, okay? A real interaction between two masses. What if, right, we want to understand, right, the property of that gravitational field without considering any particular mass? So we do that, right, by considering first, right, this idea of contour line. You see, when you have a mountain there, right, the contour line already give you a sense, right, of the difficulty in scaling the mountain. It doesn't matter, right, whether a human is there scaling the mountain or not. You look at the contour line, you know, oh, it's hard, okay? Especially if the contour line, right, as you go from 2,000 to 3,000, you know, oh, I have to scale by this amount. It doesn't matter who is scaling it. Yeah, if I am scaling it, right, and I'm 60 kg, I know that I will need to do or increase my GPE by how much, because I know the contour line is 2,000 to 3,000 meter, so I can calculate. But another person who is 80 kg can also calculate his own GPE. So the idea of the contour line, right, which is something inherent, okay, to the mountain, is important, right, to study, because, right, it's more generic. Or we can study the mountain, not study the person and who is doing the climb on the mountain. Yeah. So in a sense, right, these contour lines, right, are also something to do with GPE, or it's like a factor of your GPE, or rather GPE is a factor of this contour line. Because you times contour line times mass times G, you get a GPE at a point, or in the MGH version. Yeah. Let's now, right, consider this idea of contour lines, right, of Earth. Okay, we call this, right, contour lines gravitational potential. So suppose, right, I have a particular ball. Okay, this ball, right, has a GP with Earth, okay, as a system of this amount. Another ball, bigger one, the GP is another amount. Okay, another ball, another amount. So we want to ask, right, what is intrinsic? Because you see, these GP values, right, all depend on the mass of the ball. Yeah, they could be different, but they could be different for different reasons. For example, right, GP of the tennis ball could be bigger than the GP of the soccer ball. Sorry, it's the other way now. The GP of the soccer ball, right, could be bigger than the GP of the basketball. Although soccer ball is like smaller, right, than basketball, but it's further away. Okay, So how do we tell, right, what is the thing contributed by, how do we remove, right, the contribution of the mass that you put there? So this, once again, back to the contour line idea. You say that I expended how much energy in climbing this mountain. You expended a different energy in climbing the same mountain. But you may be carrying more load, I may be carrying less load, so on. How do we discount away this fact and find out, right, the truth about the mountain instead? So that's where, right, the contour line idea come about. So without further ado, right, you see, we have now 4 balls and their respective potential energy. So if we take away everything that's in front of the mass of the object, right, and call it this simple phi, which actually is the potential, then, right, we can actually know something about these lines per se. Okay, I go back one slide. You see, the potential energy of the ball, right, is equals to Gmm over R2 times the MB. Okay, so you take everything in front, you call it phi, then it's just phi times MB. Same for the tennis ball, it's phi times MT. So now you can come up with, hence, right, a value of phi2, or for this radius R2, that is this amount. Okay, and this phi, right, hence describes, right, the value of the contour line, or the value that you assign to these Earth gravitational contours. Okay, and that's the formulation. So what is the gravitational potential? The gravitational contour lines will be the potential energy divided by the mass. Full stop. Okay, and the formula, right, will be given by this, or contributed by a particular mass. And suppose, right, you have I'll talk about that later. Now, right, let's explore, right. See, on the map, right, when you look at contour line, you always see them, right, at equal interval away. Yeah, 10 meter, 20 meter, 30 meter. And the closeness of the contour line, right, tell you something about the steepness along that particular slope. Okay, for example, right, you see a mountain. This mountain, right, is gentle on one side, steep on the other side. Okay, so you see the map, right, one side the contour line will be far apart, the other side, right, contour line will be close. Because it is going from the same ground level up the same mountain, right, so the number of contour line will be the same, or maybe it's 0 to 1000 meter. But, right, the ease of getting up, right, will actually be different. Yeah, right now. And the lines are always, right, drawn such that they are equally spaced. Sorry, not drawn there. Let me rewind myself. The lines are not equally spaced, but the lines are always drawn, right, in equal interval. Suppose, right, we want to study the equal interval lines, right, for Earth's potential. We will realize, right, by the math, because it's a 1 over R relation with the separation, right? So if you have for example, at Earth's surface, right, you call it 60. How we know this is 60? Calculate one, because you know the value Gm over R. Okay, so this is 60, and it's not just 60, 60 times 10 to the power of 6 is a mega. Then, right, if you want to say, oh, where is the 48, which is like 12? Why do you choose 12? I forgot. Okay, just arbitrary one. You can choose 50 also, and then you choose minus 40 and so on. But now we are going in graduations of 12. So 36 will be here, okay, at this point. Yeah, then 24 will be here, and so on and so forth. Now you can see, right, that the contour lines, right, are actually not equally spaced. The equipotential lines, right, are spaced out differently in space. Here, right, it's very hard to climb because two contour lines close. Here is easier, contour lines are far. Here even easier, contour lines are further. So you see, closeness of equipotential lines, right, tells you how easy it is to climb. And what do we mean by easy? Oh, it means, right, the force that you are working against. Okay. So if you are trying to escape out from Earth, right, here is the most difficult to scale. Oh, here is getting easier. Here is getting easier. Here is getting easier. So see, the further you go away from Earth, the easier it felt in terms of the force you need to exert. Yeah. Now, doesn't this sound familiar? Because we already know, right, that F is equals to Gm over R square, or Gmm over R square. So you see, this is the same, or these are the same conclusion as before. We know when R increase, the force decrease. But here, looking from the angle of contour line, right, same conclusion, just as powerful. Okay. Oh, now, right, another thing to say about these contour lines is that going from one point, right, one line to another line, right, okay, is a path independent process. It doesn't matter, right, which path you go, as long as you start from the same place and end up at the same spot, you will have done the same amount of work or change your potential energy by the same amount. So that's yet another very useful thing. Yeah. So as it's the same. Your friend, right, go up the challenging slope to the top of the mountain. You go up the gradual slope. End up, right, you will have done the same work because you start from the same contour line, end up at the same contour line as your friend. Okay. We call this, right, we give this property a name. This kind of property is called path independent. Okay. Where you get there, how you get there, how you get there, not important. Where you start, where you end, important. That's all it matters. Now, right, we are going to further use the idea of contour line, right, to help us appreciate, right, the nature of Earth's gravitational field. Suppose, right, we draw the graph of potential against R, right, of Earth, and we just choose any random axis. You got to realize, right, that there are, like, you can choose east to west where you are, north to south where you are, any direction. Okay, it's just any one direction out towards outer space and the opposite backwards to outer space in the other way. So you choose any of those axes, right, and you draw out potential against R. And you should expect, right, there's no preference to the R because, right, in both direction, it's actually positive R. So here I neglect, okay. So here is also like that because, right, that there's no such thing as minus R. It's just R in a different direction. And we draw that graph, right, it turns out that this Earth, right, is actually setting up a set of contour lines which are invisible to us, or in terms of the gravitational potential. Okay, and these contour lines, right, you see, what's the nature of it? Suppose you draw out the equipotential values here. So just now, right, at Earth is 60. So let's say this is 50 and this is 40. It's difficult for me to put in a minus sign and write. So I'll just, and so on and so forth, 30, 20, 10. Then you see, right, the distance, right, that they take to get to the next graduation mark. See, for 60 to go to 50, not too far. For 50 to go to 40, right, like sort of further. 40 to get to 30 is even further, and so on and so forth. And you can see that is essentially, right, what this green slope is about. This green slope, right, is like a mountain. You're like starting from a valley, okay, the bottom of a valley. To both sides, right, you see this mountains feature. You're in a canyon. So you can choose to climb either side. Just look at one side. You notice, right, this slope, right, is not an even slope. It's like steeper at the beginning, gentler, gentler, gentler. It's like a plateau. Yeah. Okay, spell wrongly. It's a L A T E A U. Oh, it's a plateau here. Yeah. No, so now, right, let's imagine, right, we have this canyon, we are trapped in the middle of this canyon. We want to get to the side, because nobody wants to be in the middle of canyon. So you want to escape this canyon, right? So being a Teletubby, the way you go about doing that is to just propel yourself and you roll up the slope, yeah? So suppose, right, you gave yourself an initial speed that is less than the escape speed, okay? Then, right, what will happen? You simply cannot escape now. So let's watch it again. You cannot escape, you'll fall back down. So what does that mean on this graph? It means, right, at first you are here, you give yourself a KE, or divided by M, or you have a particular KE, but let's divide it by M. Just like how, right, potential energy divided by M gives you potential, K divided by M gives you a quantity, right, that you can relate to potential. Yeah, so there is a certain amount. So if you don't have enough KE over M, then you just simply, right, roll up to a certain point and roll back down. So how much do you possess? You possess this amount, okay? Not enough. To escape, right, you need to have this amount. So any amount, right, that you try, and it's just this, denoted by the length of this arrow, that is the amount of KE over M that you have. You simply cannot escape. You get trapped. Okay, you roll up and come down. Similarly, right, if another Teletubby, at first it's like here, on this slope, or this guy here, released from outer space. So he's going to go all the way in. So what will, how do we perceive, right, the speed that he will gain by the time he comes in? You see, it's like this Teletubby, right, from here, roll down this slope, drop into the canyon. Yeah. So he will end up, right, gaining this amount of speed. And this, right, tells you that, oh, in fact, right, see, this thing is really like a trap. Someone, right, or Teletubby that not careful, right, walk along the slope, or may fall in. Someone who will fall in really, right, hard to come out. So gravity is actually like a trap, like a well. Yeah. Just now we drawn this line. Let's see them again. In terms of the distances, so you can see, right, if we increase by the fixed amount in terms of potential, the distance that to get to the next fixed amount line, right, the equipotential, regular interval equipotential lines, you actually need to travel further. Or in a different way of thinking about it, right, it's easier and easier in terms of force. Yeah. Or to run up this slope is easy. To run up this slope is difficult because it's very steep. Oh, and that steepness of the potential, right, tells you the force. Okay. So, right, in a sense, this visualization, right, will tell you that what gravity is doing, right, it is sort of, right, like making a dent, okay, in the fabric of space-time. This is too abstract already. Okay, this one is relativity, but it gives you appreciation. Then, right, why do things, right, like for example, moon orbit around Earth, right? It's because, right, like Earth make a dent, right, on the space-time fabric. Okay, so things that are nearby, right, tends to roll down the space-time fabric slope. Okay, and end up, right, getting trapped. Yeah. So no big deal. Okay, it's a skip. So now, right, we have gone through so many terms already. So let's do a quick recap. We have forces on one side, force, and field strength, which is a force, but it's a per unit mass force. On the other hand, we have potential energy and potential energy per unit mass. So this is also an energy. So one side is all vectors, the other side is all scalar. Yeah. And we know how to relate to each other. So it's simply just like this. Okay. But we haven't done any relationship, right, across the boundary, which we'll do in a while. Okay. Going back to relationship between the F and U, we can recall, right, the formula: potential energy is equals to work done by the external force in going from infinity to that point. So you can rewrite, right, this as this. Oh, am I right to say that? Yeah, you can rewrite this, and therefore, you make this connection that the external force is actually equals to minus G. Okay, yeah, we know that from here as well. So that means, right, Fg is equals to minus du over dr. Okay. Repeat the idea. It starts from here. Okay. It tells you that if you differentiate both sides of the equation, du over dr is F external. And we know F external is opposite of Fg, negative Fg. Therefore, Fg is also negative du dr. So this tells us the relationship between the force and potential energy. So if you divide by mass on both sides, right, you simply get the relationship between field strength and gravitational potential. Okay, so very neat. These two, right, are the same thing, just a factor of m away. Okay, so while this, right, describes the relationship, right, the interaction between two objects, this describes, right, the property of the field. Okay, because you don't have anything there. It's just talking about the field strength and the potential. Okay, and you see, what is the phi over the r? You recall back, right? We are looking at this curve, right? Oops, too fast. So you see, we are looking at this curve. This is the potential energy or potential plateau, right, or on the side of the canyon. So the slope tells us, right, how difficult it is to surmount, what kind of force we need to exert. Yeah, and you see, that's exactly the word, the slope. Yeah, you see this curve, right? It looks like is a non-uniform slope. The steeper it is, the harder it is to surmount that part. So Fg is equals to the negative of the gradient of potential energy. So you see, the words, right, already tell you the meaning. It's the negative of the gradient of potential energy. Or how steep this curve is tells you how large the force is at that point. But why is there a minus sign? Because, right, see, this is a positive line or positive gradient line. This is also positive gradient line. In fact, right, it will be positive all the way. Yeah. But where's the force? The other way, inwards. So in this notation, right, if outwards is positive, given by the arrow here, then a force that's inwards must carry negative. Is it provided by the formula? It is. Okay, here. Same thing go for potential. I'll skip this slide because it's communicating similar idea. So now, right, we complete the picture. This is the relationship between things on both sides. Yeah. Final example before we wrap it up will be example 10. We have a Earth-Moon system. So here, right, what we are trying to do is to find out how does the potential landscape, okay, look like. So you see, just now we studied, right, the potential canyon, okay, due to one Earth, just due to one planet. But then, right, what if on some way out there, right, or there's another mass out there, okay, that mass, right, will also create its own canyon, okay, around it. So that will mean, right, that what results from this must comes from the individual contribution. So we have two of these planets, right, okay, creating their own set of canyon feature. But then what is come out of it is the net. So the resultant, right, phi will look like this. Okay, and it's a finite value, by the way. Here it doesn't look like it's cutting, it's like it's a finite value. Okay, here is also a finite value. And we know, right, that the potential energy is equals to mass times phi. Yeah. So suppose you know you have a particular object, maybe a rock, 100 kg. So if the rock, right, is to be, or don't say the rock, maybe a space shuttle. Okay, a space shuttle, right, you want to go and reach moon. How much energy, right, must it possess? You can use this graph because, right, here, let's say you have a certain value. Let me just give you an arbitrary value, minus 100. Okay, and let's say this value here is minus 20, and the other value here, which is the one on moon surface, is minus 30. Then, right, how do we interpret this? For the guy, right, going from Earth towards moon, how much energy does he need? Well, you see, he just need to enable himself to get up this red color slope, okay, to the top. And the top, right, has a value of minus 20. So the net, the change in potential, right, is plus 80 to get to the top. And that's all he need to worry about if you want to get to moon. Because, right, once he can get to the top, go to moon, right, is easy already. It's just rolling down, rolling down the hill on the other side. So he need to climb on the first half and just roll down this slope on the other second half. So on this picture, right, this man or this space shuttle just need to be concerned about getting to this point. Once you get to this point, right, here, right, will be taken care of by gravity. So here, right, you see, in other words, right, as you go from A to B, seems that you are working against gravity. Going from B to C seems like you are working with gravity. Since you're working with gravity, you don't need to do anything. Just switch off and relax lah, and just cruise there. Just be sure don't crash onto moon in the last part. Yeah. But then getting from moon to Earth, right, is easier. Okay, you see, getting from moon to Earth, right, is going from minus 30 to 20. So here, right, the change is only 10. Whereas here, right, the change needed, right, is 80. So it's asymmetrical. And this is often seen, right, in those kind of space movie, or even, right, the real Apollo mission, although it's a lot more engineering. But, right, you see, when you go from Earth to moon, right, you have the huge booster rocket, okay, spectacular TV coverage, right? See, as the rocket launch, wow, flames throwing out from the burning of the fuel, so elaborate. And all these rocket boosters, right, the fuel tank, after the rocket reach a certain altitude, right, you will disengage. All this fuel tank, right, will just fall off and drop into the ocean. Okay, whatever that fly out, right, is only the main thing itself, or the main shuttle. Then you must ask, right, how come on the reverse return journey, don't need one? On moon, they never park the rocket booster there, what? So how come on moon, right, you can just fly back easily? That's because of it's easier from the other direction. From Earth, right, you need to surmount such a huge gap. You need a lot of initial speed, initial KE. Whereas starting from moon is very easy. Okay. Finally, right, how does a force against R looks like? I'm saying force, but here I show G. Doesn't matter. G is a per unit mass force. So it's just like saying, right, what's the force on a 1 kg? Yeah. So everywhere, right, to this point, you see, if you apply the formula, right, oops, the G is equals to minus the phi over ER. Sorry, yeah. Then you can see that here, right, the gradient is 0. Oh, so it means 0G. Here is all positive gradient, and here is all negative gradient. Means, right, here is all positive G, and here is all negative G. Okay, makes sense, right? Because when you are nearer to Earth will attract you stronger. So the net G will be towards Earth. When you're nearer to Moon, or the net G will be towards Moon, which is positive direction. Then at the neutral point, and neutral point have to be closer to Moon because they are playing tug of war. Okay, but Earth is much stronger. So you see the Gm over R square, right? At what point will the two G be equal but opposite direction? Must be closer to Moon because it has a smaller mass. So the smaller mass over a smaller R square, bigger mass over a bigger R square. Or at that point, 0. Okay, so this graph, right, got meaning one. So here's positive, here's negative, denoting the direction of the gravitational field. And with that, right, come to the end of this portion. So before we end, any question, anything that you need extra explanation on?
Mr. Kwek, can you explain the part on why you connect G to gravitational potential, right, is using the gradient and not just times 1 minus 1 over R? Like, why do you have to compare between 2 points?
Okay. No, I believe this part or the because maybe here. Is it because, right, you should ask, right, why should you times or divide by 1 over divide by another R to give you F? Because what's the reason behind it? There's no reason. It is only mathematically similar. You can see that one is Gm over R, one is Gm over R squared. They look mathematically similar, but is there any physics behind that similarity, which is divided by the 1 more R? Don't have. The real physics, right, is the connection. It must be based on the real relation. The real relation here, right, is a relationship about work. Okay, so the potential energy is force times is the area under the force and distance graph. So which is this part here, or integrate force with respect to distance. That is the relationship between these two. So it turns out, right, that when you write that, I think it's the, let me escape the presentation. Yeah, it turns out, right, that when you write it out, it happens to be similar. That is just a consequence of how when you integrate 1 over R square, you get minus 1 over R. Okay, the relationship is an integration, not a times R. Yeah, there's no basis behind the times R. And in problem solving, right, could you just do a times R to get whatever that you want to solve? Often not. If there is some cases you could, right, it's because the circumstances somehow just need you to find the value or something you can just manipulate, but not something that you should use, right, as a matter of concept. It's a hack rather than a conceptual thing allowing you to do that. Yeah. Anyone else have other question or whatever I explained, does it address your concern, Ian? Anyone else want to clarify? Okay, if not, try. Thank you for your time. If you wish to clarify one-on-one, you can just stay back in the Zoom call. Have a great day and have a good start to school next week.